Okay, so let us continue with exercise 20. Now here we are given a field F. We have to prove that F1 is not isomorphic to Fn for some integer n greater than 1. So this is the space of all 1 tuples over F, and this is the space of all n tuples over F. In other words, this is the space of all vectors with only one component over F, and this is the space of all vectors with n components over F. And in part B, we have to prove that F2 is not isomorphic to F3. So let us see A first. The proof is by contradiction. So suppose there exists an integer n greater than 1 such that F1 is isomorphic to Fn. So that means there will be an onto isomorphism between these two vector spaces. Let T from F1 to F2, Fn be an onto isomorphism. Recall that for us, isomorphism means a homomorphism that is one-to-one. If we want it to be onto, we have to specifically mention it separately. But in some other books, isomorphism itself means a homomorphism that is both one-to-one and onto. That's not the case for us. Okay. Now since T is onto, there exist scalars alpha and beta such that alpha T is this vector, this n tuple, and beta T is this n tuple. These are two n tuples in Fn, so they will be, since T is onto, so they will be T images of some vectors from the domain space F1. Now here I should say something about this notation alpha T and beta T. You see, according to our definition, F1 is the space of all one tuples. So strictly speaking, I should not have written alpha T here, but I should have written this instead. This is a one tuple which has only one component, and that is alpha. But this map between the field and this space, which sends say any field element lambda onto the one tuple whose only component is lambda, this map is a vector space homomorphism that is one-to-one and onto, which is extremely straightforward to show. And note that just like this is a vector space over F, the field itself is also a vector space over F. So as vector spaces, there is no essential difference between this one and this one. So that's what we are using here. Instead of writing alpha within brackets, which is a one tuple, we are simply writing the component itself. Now you may ask me, why should we do that? The reason is that the more we handle with these things, the more we should learn to identify things like this. There is no essential difference between F and F1 as vector spaces. And in fact, that is the philosophy of isomorphisms, right? You have two groups, or you have two rings or two vector spaces that are isomorphic to each other. There is no difference between them as far as those group structures or ring structures or vector space structures are concerned. So it's enough to study only one of them. The others are, you know automatically about the others. Exactly similar things are going to happen in the other spaces or other structures. So that's why it's a good practice to not distinguish between trivial things when going through these things. And the more you, the deeper you go into the subject of not just algebra but in other parts of mathematics also, you will see that many things, identifications like this where we don't distinguish between these two, that will occur more and more frequently. Okay, so let us continue. So we have now got two equations like this. Okay, now can alpha or beta be 0? Clearly they cannot be 0, because any homomorphism maps the 0 vector onto the 0 vector of the second space, and these are non-zero vectors. Since T is a homomorphism and these are non-zero vectors, I am not writing that because that's evident. We must have alpha not equal to 0 and also beta not equal to 0. Thus, what is 1t? 1 is the field element 1. You can write 1t as alpha inverse times alpha t. Now this is not the one, of course you can think of it as the one tuple also consisting of this single element alpha inverse alpha, but that's not what we mean when we are writing brackets. We are just simply writing them within brackets to show the fact that t is being applied on this whole thing. Now, because we are identifying field elements with the corresponding one tuples, so here you can in fact think of alpha inverse alpha not as a product of two field elements, but as a product of this scalar alpha inverse and vector alpha. Then, because T is a homomorphism, this will be alpha inverse alpha T by the second condition in the definition of a homomorphism. So this is alpha inverse this vector and similarly 1t is also equal to, because beta is also non-zero, and that is equal to, you will get the same conclusions or same equations or same calculations, if instead of writing simply alpha t, you write 1 tuple alpha t, then also you will get the same thing. Okay, so this is equal to beta inverse 0, 1, 0, and the others are all 0. So that is equal to 0, beta inverse 0, and so on to 0. So both of these vectors, this one as well as this one, are equal to 1t. So they are equal. This implies and hence, now what do we get from this equation? That alpha inverse is equal to 0 and beta inverse is also equal to 0. But this clearly is not true, because if alpha inverse is 0, then you multiply on both sides by let us just go one more step and show why this is not true. But then we just need one of these two equalities to show that things have gone wrong. But then 1 is equal to alpha inverse alpha, that is equal to, if alpha inverse is 0, equal to 0. This is not true, but why? Because we are in a field, and in a field, by definition, a field is a ring in which the non-zero elements form an abelian group under multiplication. So if 1 is equal to 0, then there is no non-zero element in the ring. So it can then not be a field. Why this condition implies that the ring has only the 0 element, that I leave to you. Okay. So the thing is that in a field, the unit element 1 is always different from the 0 element 0. This is not possible in the field F. In a ring it is possible, and there is only one ring where it is possible, that is the 0 ring. In the 0 ring, the 0 element is the additive identity, it's also the multiplicative identity. Okay, so this is not possible in the field F. Hence, our supposition is wrong. That is, f1 is, that is, there is no such integer for which f1 is isomorphic to fn. Now after this we have part B. I wrote one solution at some point, but today I found that there are some, the solution is not wrong, but it's not very satisfactory in some sense. So what I will do, I will leave this one for now. Okay, we will come back to it when I find a satisfactory solution. You will see why it is not satisfactory in the present form. I will tell about it then. Okay, so we keep this one hanging and we move on to the next one. The last one, in fact, in this set of exercises. If one uses the theory of vector spaces, I mean the things that are coming which we have not seen yet, then this exercise can be answered in just one line. However, we don't have that, so we have to do all these things, which is the theory of dimensions. 21. If V is a vector space over an infinite field, F, prove that V cannot be written as a set-theoretic union of finitely many proper subspaces of a finite number of proper subspaces. Okay, so if the underlying field of scalars is infinite, then this exercise is claiming that V cannot be written as a union of finitely many proper subspaces. So in the solution we will suppose that it can be written in that manner, and then we will derive a contradiction. Suppose V can be written as a union of these W's, where each Wi is a proper subspace of V. Okay. We assume without loss of generality that W1 is not a subset. W1 is not contained in the union of the other subspaces, and the union of the other subspaces is also not contained in W1. In fact, for that second one that I am saying right now, we don't need this. That is already true because the Wi's are all proper subspaces. This and this is also not contained in, not a subset of W1. How are we assuming this thing? You see, if W1 were contained in this union, then there was no point writing W1. I mean, there was no point writing W1 in this union because it will then have been engulfed by this other part. We could have written W2 union W3 and so on because W1 will be lost inside. W1, there is a point to write W1 here. You need to write W1 here if there is at least one vector in W1 which is not in the other Wi's. Then only it makes sense to write W1 here. Otherwise, you can write W1, but that is purposeless. So that's how we are assuming this. And this is also not entirely contained in W1 because if that was the case, then this entire union would be equal to W1. But then W1 will be equal to V, contradicting the fact that all the Wi's are proper subspaces. Okay, so this second thing actually is already true. We don't have to assume it separately. Okay, now because of all these things, choose elements say U belonging to W1 minus the union of the other W's and phi belonging to the union of the other W's minus W1. Our assumption that none of these two sets is contained in the other allows us to choose such vectors. I mean, there are vectors, so we have chosen two such vectors. Now consider the set A. Now in this set we are going to consider vectors which look like this: phi plus alpha u, where alpha varies over the field. Okay, we are not saying this A is a subspace of V or anything like that. It's just a set where the vectors look like this. Now we are going to define a function f from f into A which maps the field element alpha onto the vector v plus alpha u. Okay, clearly f is well defined and onto. F is well defined because for every alpha the image already the image belongs to A. In fact, the elements in A look like the images. So the outputs are in A, and for a given alpha this output is a unique vector in A. So there is, I mean, we are not getting two different outputs or anything like that. So F is well defined, and ontoness is obvious. You take any element from here that is coming from alpha via F. Okay, so F is well defined and onto. Now we want to claim that F is also one-to-one. For that, let alpha 1 and alpha 2 belong to the field such that alpha 1 F is equal to alpha 2 F. Then phi plus alpha 1 U, which is alpha 1 F, is equal to phi plus alpha 2 U, which implies alpha 1 minus alpha 2 U equal to 0 using the elementary vector space axioms. Now do you get from here the fact that the vector U is not equal to 0? We are going to use that now. And in fact, we simply write, since U is not equal to 0, we have alpha 1 equal to, actually alpha 1 minus alpha 2 is 0, which means alpha 1 is equal to alpha 2. And this itself comes from one of the elementary results, the very first result that is true, those elementary calculations are true in a vector space, that result, where for example we proved that the scalar 0 times any vector is the 0 vector, that result. But the question is, why is U non-zero? U is non-zero because you see U has been chosen to be a vector in W1 that is not in these spaces, not anywhere in the other WIs, and the other WIs are subspaces. So they contain the 0 vector. So since we are choosing U to not lie in any of the WIs, so U must be non-zero because 0 belongs to all the WIs. That's why. Thus, F is also one-to-one. This shows that F is a bijection. F is a bijection between A and F, or F and A, same thing. Okay, now we are going to see what happens when one considers these intersections. The intersections of A with the Wi's. And we are going to first of all see this one. We will suppose that this intersection is non-empty, that is, there is at least one vector which is in A as well as in W1, and we will arrive at a contradiction which will prove that this intersection is empty. And then we will also say something about the other intersections. So let us see. Now suppose this intersection is non-empty, that means there is something. So we can choose an element or choose a vector, whatever you may call it, W belonging to A intersection W1. Okay, now since W belongs to A, so W will look like this. Then W is equal to phi plus beta u for some scalar beta. Okay, now what? Since W1 is a subspace, we have phi equal to W minus beta u, which we are getting from here. This belongs to W1. Why? Because you see, we originally have chosen u from W1. So u is a vector in W1, and now because W belongs to A intersection W1, so W is also in W1. So this is a combination of U and W. So it will also belong to W1. That means V belongs to W1. This, however, is a contradiction to this choice, because according to this choice, V is not in W1. But this is a contradiction. So our last supposition above is wrong. That is, A and W1 do not intersect. They are disjoint. Next, suppose that for some integer I lying between 2 and n. So now we are going to say something about the other intersections, the intersection between A and Wi. So that's why we are choosing I like this. We have the number of elements in this intersection greater than or equal to 2. This also will be proved incorrect because we again will run into a contradiction. So that means we are assuming that now there are at least two vectors in A as well as Wi. So that means we can choose two vectors, and two such vectors are chosen like this. So because the vectors are going to be in A, so we can already choose them to be in that form in which we have the elements in A, that is V plus alpha 1 u and V plus alpha 2 u. We considered alpha 1 and alpha 2 previously when we showed that f is a one-to-one function, but that is something else. Okay, that is gone. So this is something else. Alpha 1 and alpha 2, these two belong to A intersection Wi, where to ascertain that we have chosen different vectors, alpha 1 and alpha 2 must be different. Are distinct elements in F. They are distinct scalars. Then since Wi is a subspace, we have u equal to 1 divided by alpha 1 minus alpha 2. Because alpha 1 and alpha 2 are different scalars, so their difference is a non-zero scalar. So it will have a multiplicative inverse in the field. U, and this can be properly arranged, and one can write in its place V plus alpha 1 u minus V plus alpha 2 u, so that after cancelling these two v's, you are left with alpha 1 minus alpha 2 times u, which is this. Now this belongs to Wi, this also belongs to Wi, so their difference belongs to Wi, and if you multiply them by this scalar, that product also belongs to Wi. So this belongs to Wi. This, however, is again a contradiction because we have chosen u to be a vector that is in W1 and not in the other Wi's. But this is a contradiction. Previously we got the contradiction in the choice of V. Now we are getting a conclusion which is contradicting the choice of U. So our last supposition or latest supposition is wrong. That is, the number of elements in this intersection must be less than or equal to 1 for all j varying from 2 to n. So what is the ultimate conclusion of all this? We have thus shown that A intersects each wj at most one point, and A in fact does not intersect w1 at all. And what about the other wj's? It may intersect, I mean there may be a common vector, but if there is a common vector, then there is only one common vector. A intersects each wj at most one point. Thus wj means here j is no longer varying from 2 to n, okay, all the things are included. Thus okay, no, but before saying what I'm going to say now, we should also consider something else. Since A itself is after all a subset of V, and V is nothing but the union of these w's. So that means A will have at most one element from each wj, and there is nothing else in A. Those are the only elements in A. That is because A does not have any part that is outside of all these w's because of this containment, because of this inclusion. Hence, what will be the order of A? A does not intersect with w1. A may or may not have an element common with w2. A may or may not have an element common with w3. In the extreme case where A has elements common with these wi's, you will have at most n minus 1 elements in A. It may be less than that also. So now what do we conclude from this? We conclude the interesting fact that the set A is finite. This implies A is finite, but we already have a bijection between F and A. So if A is finite, then F is also finite. And hence F is also finite, which directly contradicts the hypothesis that F is an infinite field. Since F is given to be infinite, our first supposition itself is wrong. So the original vector space cannot be written as a set theoretic union of finitely many proper subspaces. So V is not the of finitely many proper subspaces. This completes the solution. And it also, I should not say completes because we have left that one, but the activity is over. We have gone through all the exercises in this set of exercises. So let us now start the next section. Section 4.2, linear independence and basis. Now in the beginning itself, we are going to recall two examples. Example 413 from this section. and the other one is example 414. In example 413, the space was the space of all polynomials over a given field F. And in example 414, the space was, I think it was written as Vn or something like this, which consisted of all polynomials of degree less than n along with the zero vector. The zero polynomial. Now, although both of them are vector spaces, but there is one difference between these two. You see, any general element fx looks like this. Say alpha 1 or okay, in fact let's keep it simple. Alpha naught plus alpha 1 x plus alpha 2 x square plus etc. plus alpha n x to the power n, or we may confuse this n with that n. So let me take m, where these are coming from the field and what else is true, this m can also change. This m is in fact any non-negative integer, but the elements in Vn look like this: beta naught plus beta 1x plus beta 2x square, beta n minus 1 x to the power n minus 1. Here this n minus 1 is fixed, it does not increase, okay, and the betas of course are again coming from the field. So the difference is that in this second space all the elements look like this. In a sense, they are being generated by these vectors. In what sense, that we will now make precise. These are also polynomials. In fact, they are monomials because each one of them has only one term and they belong to, in fact, they of course belong to fx, but in particular they belong to Vn, so that using only them and some scalars, an equal number of scalars, this type of combinations are giving us all the elements in Vn. And in these combinations, if we call these things as coefficients, when you are treating this as simply a polynomial, these are coefficients, but now the scalars can also be called as coefficients. These coefficients are coming from F, and these are vectors coming from the vector space Vn, and this is a combination where the vectors have been multiplied by the scalars and such products have been added together. Okay, so that gives you another vector, of course, since this calculation is taking place in a vector space. So the closure properties tell us that this is again a vector in Vn. Now these vectors are finite in number. Okay, they have the power to generate the whole Vn in this sense, but in this space you cannot find such a finite set. which is also easy to show. For example, suppose someone claims that no, there are in fact in this case also, fx also, there are finitely many polynomials which can generate the whole space. If one considers such combinations, then we will run into a problem. Let's see what. Suppose you have polynomials. See, in this case we have these concrete polynomials. In this case we don't know. Someone is claiming that there are. They also don't know what the polynomials are, but they are claiming that some finitely many polynomials are there. Suppose f1x, f2x, etc., frx in fx such that all the elements in fx look like this. Again, we are considering such a combination, this type of combination. Suppose someone has claimed this. How do you refute this claim? How do you say no, what you are saying is not correct? The technique is this. You see, clearly the polynomials, there is no point in taking a zero polynomial, the zero polynomial here, because the zero polynomial will not contribute anything to this combination. So it will just simply, once you form a combination like this, if you have some zero polynomial here, that will vanish. So we can safely assume that because we want many polynomials, as many as we can, to sort of generate this whole space fx, so we can safely assume that none of these fi's is the zero polynomial. So because they are not the zero polynomial, so each one of them will have some degree. So suppose the degrees are n1, n2, etc. in R. Now these are all non-negative integers, so there will be a maximum. This will also be a non-negative integer. So no matter how large this maximum is, you can always choose a positive integer n that is larger than this, because positive integers are unbounded above. Now you consider this polynomial. It's also there in fx, because here there is no restriction on this m. You can choose m as large as you want. So this is also a polynomial in fx. Now do you think this can come in this form? No. Why? You see, multiplying a polynomial by a constant which is say non-zero does not change its degree. So the degree of f1 is n1, the degree of alpha 1 f1 is also n1. Similarly, the degree of this is also n2. Yes, of course, if your alpha is 0, then it becomes zero polynomial, but in that case there is no point in considering it at all. So we are also additionally assuming that all the alphas are non-zero, just like these polynomials are non-zero. So the degree of this product is n2, the degree of this is nr. Now when you add these polynomials, what will the degree of the sum be? The degree of the sum will be the degree of that polynomial that has the largest degree. For example, if you say add these two polynomials, minus 5. Then the sum is x cube plus 2x square minus 8. So this one has degree 3, this one has degree 2, but the larger one contributes to the degree of the sum. So here also the degree of this polynomial will be the maximum of ni. So clearly no such expression like this can ever be equal to x to the power n. So no matter how many polynomials you take here, if the number of polynomials is finite, they cannot generate this space if we consider only combinations like this. They don't have the power to generate this space. So do you see that this space is, in this sense, too large for finite sets of vectors to handle? This space is much smaller than this space in this sense, that only finitely many vectors are enough to generate it in this sense, whereas here no finite set, no matter how many elements it has, can generate fx. So we are now going to make these things precise, and we are going to study spaces which are not too large, which are not like fx but like vn. Okay, so that is our aim now. In the very beginning, we should make precise this notion of combinations. What type of combinations are we talking about? They will be called linear combinations. You already know that, but we are going through the things systematically. Okay, so the very first definition is this. Let V be a vector space over some field f. In linear algebra, or in the theory of vector spaces in the present form, we have said that we are going to study spaces like Vn, but those very large spaces we will handle in functional analysis. Okay, we will see how. We will need additional structures there, some sort of topology on those spaces. Okay, if V1, V2, etc. up to Vn belong to V, then any element of the form alpha 1 V1 plus alpha 2 V2 etc. plus alpha n Vn, where these alphas are coming from the field of scalars, is called a linear combination of these vectors over the field F. Okay, this is a technical way of saying when you see over F, it means that the scalars are coming from F. You may ask, why do we need to write this separately? Because F is all we have. Here there is a vector space and there is the underlying field of scalars, so of course the scalars are going to come from F. The answer to your question will be, in some situations we may have multiple fields. Okay, in such cases we should write over F. It will tell you from where you are taking the scalars. Okay, so that is called a linear combination. So for example, in Fx, this is a linear combination of these vectors. Okay, so that is pretty straightforward. Now, although we have this part over F, this phrase, but we are not always going to use it. Specifically when the underlying field is understood and there is only one field, or maybe there are more fields, but in some situation you know already where the scalars are coming from, then we will drop this over F part, since we usually are working with some fixed field F we shall often say just simply linear combination. Rather than linear combination over F. Similarly, sometimes we will just simply say vector space instead of always saying vector space over F. That is also written here, I am not writing it again. Okay. Now next, there is another notion, linear span. Once you have the notion of linear combination ready, we can then define linear span. And it goes like this: if S is a non-empty subset of a vector space V, the linear span of S denoted by this symbol L of S is defined to be the set of all linear combinations of finitely many elements from S. Okay, they have written linear combinations of finite sets, same thing, same meaning. Finite sets of elements of S. What is the meaning of this? Okay, suppose, let us take one example, concrete example. Let's take that itself, fx, but instead of taking some arbitrary f, let us take the space of all linear polynomials. Okay, now in this, let us consider the set S to be the set of all polynomials that look like this. Such that f of x is not equal to 0 and say degree of f of x is greater than 0. So, clearly this is a subset of Rx. And it's definitely a non-empty subset, because S must be a non-empty subset of the vector space V. This is our V now. Now, what is the linear span of S? The linear span of S looks like this. The elements in LS, a general element will look like this. Where these polynomials f1, f2, etc. are coming from S, and thus coefficients of course are coming from the field, which in this case is the field of real numbers. So let's match the two things. The linear span of S denoted by L of S is defined to be the set of all linear combinations. These are the linear combinations. They will look like this, of finite sets of elements of S. This is a finite set of elements of S. This set can change. Its number of elements k can also change. K can in fact be 1, or k can be as large as 1 billion. It does not matter, but this set must be finite, because note that according to the definition of linear combination of finitely many vectors are only considered. We have not defined anything like this. We are not talking about any infinite sum like this. Okay, by definition, a linear combination involves only finitely many vectors. So here, although the set itself is in, because you see here if S is infinite, what do we have in S? In this particular S, we have all non-zero polynomials, neither of them is constant. Okay, none of them is the constant polynomial. So there are infinitely many non-zero polynomials which are not constant. So the set is infinite, but every time we are going to consider a linear combination of elements from this set, we are going to first of all choose finitely many elements from S, then form their linear combination. All such possible linear combinations make up L of S. Okay, so that is L of S. Your S, of course, can also itself be finite. In that case, everything is finite and there is no problem, but S itself can be infinite, but the linear combinations that we are going to consider to form L of S, they will be finite. I mean finite expressions. Okay, so that is the definition of the linear span of S. So there will be many elements in the linear span, or it will depend on the situation. Okay. Now here comes our first result. Lemma 421. You take any vector space V, you take a non-empty set S in that space, you form the linear span. This L of S is going to be a subspace of V. That is this lemma. This is a subspace of V, where we understand in this context V is a vector space and S is a non-empty subset of V. The proof is quite straightforward. Since S is non-empty, you see L of S by definition is a subset of V. But before showing it's a subspace, we must make sure that it's non-empty. That is the first condition, and then only you can verify that condition for a subspace. Since S is non-empty, this is a non-empty subset of V. Because there is at least something in S, so there will be at least some linear combination that can be formed, which will be there in L of S. So L of S is a non-empty subset of V. So now our usual subspace criterion. So we now have to consider two elements in L of S. By definition, they will look like this. Each of those two elements will be a linear combination of some finitely many elements of S, where of course the scalars are coming from the field. How many, that no one knows. Okay, so let S1, S2, etc., Sn, T1, T2, etc., Tn belong to S. Oh no, not N. We should choose another number, say M. and correspondingly scalars actually I should not have written it like this. I should have considered two such linear combinations in LS, and then I should have written where S1, S2 they belong to S and so on. But you can understand what I am trying to write here. These belong to F, so that alpha 1 S1, alpha 2 S2 plus etc. alpha n Sn, this is one element in L of S, plus beta 2 T2 plus beta m Tm. These are two general elements in L of S. Also, let alpha and beta be two general scalars. F is the underlying field, okay, that is understood. Then what happens if we form this combination alpha 1 S1 plus alpha 2 S. Let's take space and write things clearly. Alpha n Sn plus beta times beta 1 T1 plus beta 2 T2 plus beta m Tm. We are now going to, of course, use to carry out this calculation the various axioms in the definition of a vector space, which we are not going to explicitly mention. First, we have this alpha distributes itself over this combination alpha 2 S2 plus alpha n Sn, and then so does beta. Beta distributes itself over that other combination plus beta times beta 2 T2 beta beta m Tm. Then this becomes, using one of the vector space axioms, this is alpha alpha 1 S1 alpha alpha 2 S2 alpha alpha n Sn, and then the terms involving T. Plus beta beta 1 T1 beta beta 2 T2 and so on, plus beta beta m Tm. Now note that this final expression itself is a linear combination of finitely many elements of S, and those elements are S1, S2, up to Sn and T1, T2, taking all of them together. So clearly, by the definition of L of S, this final expression is again in L of S. Thus, by the subspace criterion, this is a subspace of V. So the proof is actually quite straightforward. The very nature of the elements in the linear span makes it a subspace of the vector space. Now there is something which has not been mentioned in this book regarding this thing, linear span, maybe because Herstein treats it as trivial, but unfortunately there is one particular instance where that thing is necessary. So I am now going to give another slightly more general definition of the linear span of a subset, where I say slightly more general because we already have the definition of a linear span where there is a restriction on the set S. S should be non-empty. I am now going to lift this restriction. Now my S can be empty also, and I am going to now define linear span in a different way, and then I am going to prove that when S is non-empty, our linear span and Herstein's linear span are the same thing. I say our, but it's already there, okay? It's not something I have done. Of course, it is something that is already there in the theory of vector spaces. For some reason, Herstein has either missed it or he disregarded it. Okay, so this is a definition that is not there in the text, but you will see that this definition is a very natural one. Because it's not there, I am putting an asterisk over it. Let S be any subset of a vector space V. We define the linear span. We are going to still call what I am going to define now linear span, okay, just like before, but since it's slightly different now, so instead of writing L of S, I am going to write Li of S. The linear span of S denoted by Li of S to be the intersection of all the subspaces of V containing S, okay, which looks entirely different from what we have seen linear span that the author has given, but they are related. Why I said that this definition is extremely natural, recall some notions from group theory and ring theory. Suppose you have a group, okay, in that you have a subset S. Or let's forget ring theory, because in this book we have not in fact considered the notion of subrings very much. So let's consider group. Say G is a group, S is a subset, and this is something we have already obtained. Okay. Now there is a notion, do you remember, of the subgroup generated by S. According to this notion, it is the intersection of all subgroups of G containing S. That is, S is there inside G. Now there are many subgroups in G, of course. Some of them contain S. We collect all of them together and we take their intersection. So that is defined to be the subgroup generated by S, and we have already seen that that thing turns out to be the smallest subgroup of G containing S, and we in fact used a notation like this to denote maybe that intersection. I don't remember exactly which notation represents what, but this is already there in the text. This is the subgroup generated by S. We have defined the linear span of S in a similar manner. Here we have subgroup, here we have subspace. That is the only difference. In place of group, now we have a vector space V. Still S is a subset of V, just like here S was a subset of the group. And here we considered all subgroups containing S, here we are considering all subspaces containing S, and we are taking their intersection. And we are calling it the linear span of S. Now one can proceed like group theory and show that this linear span, just like that linear span for a non-empty set S, is a subspace of V, in this case also, in this slightly general case. But that is not our aim. Our aim now is to show that this Li of S is nothing but L of S if S is non-empty, and that is why it makes sense to call it linear span, because when S is non-empty, our Li of S and Herstein's L of S are actually the same thing. But because of this definition, we now have one extra case also covered, namely when S is empty. We will see what happens to Li of S in that case when S is empty, but right now let us show this. So this lemma is also starred. If S is a non-empty subset of a vector space V, then let's now see the proof. note that S itself is contained in L of A. Keep in mind that now S, just like before, S is now non-empty. Okay. If S is empty, this is meaningless. This is not there in this book, but for us we have this. So now S is non-empty. Whatever be the case, S is contained in L of S. How? You may ask. To prove this, which we will not do, actually we will not make that a part of this proof. You take any element S in S. Now S itself is also a linear combination of finitely many elements of S, namely only one element, and that linear combination is just this 1S, where 1 is your unit element coming from the field. So this by definition belongs to L of S. So every element in S is in L of S, which is a very straightforward fact. So this belongs to, this is contained in this. Now we use the previous lemma that we have proved. According to this lemma, L of S is a subspace of V. What was the 421? By lemma 421 is a subspace of V. So now see, L of S is a subspace of V containing S, and this by definition is the intersection of all subspaces of V containing S. So clearly this will be contained in this. This is only one subspace of S containing S, and this is the intersection of all subspaces of S, subspaces of V containing S. So this will be smaller and it will be contained in every such subspace which contain S. So in particular it belongs to, it is contained in L of S. Now we have to prove the converse. For the converse, let alpha 1 S1 plus alpha 2 S2 etc. plus alpha n Sn belong to L of S, where the Si's belong to S and the alpha i's belong to the field. So this is a general element in L of S. Okay, I should have assumed this, what I am going to write here before this. Anyway, let W be any subspace of V containing S. So that means W is a subspace of V and S is a subset of W. Since S is a subset of W because W contains S, these Si's all belong to W, because they are in S and W contains S, so they will belong to W. But then, because W is a subspace, so this linear combination of the SI's will belong to W. That means this general element of L of S is there in W. Thus, L of S is contained in W. So that means L of S is a subset of every subspace containing S. So clearly L of S will also be a subset of the intersection of such subspaces which contain S. This implies L of S is a subset of all the intersections, the intersection of all the subspaces that contain S, and that intersection is nothing but Lie of S according to our definition. So that means L of S is contained in Lie of S. So we can now combine these two inclusions. We have thus proved that Lie of S is equal to L of S. Okay, so we have shown what we were claiming. So it's justified to call this slightly more general Lie of S also the linear span of S. Now let us see what happens when S is empty. Oh, but before that, we are going to use this lemma and the previous one to claim that when S is non-empty, then Lie of S is also a subspace because it's nothing but L of S. So we write that as a small corollary. If S is a non-empty subset of a vector space phi, then this is a subspace of V, and the proof, of course, it follows from the previous two lemmas. Previous lemma and lemma 421, because the previous lemma does not have any number attached to it, so small l, and this one has a name, so capital L. Okay, now we see what is Lie of phi. I should not say phi but empty set. phi is something else and empty set is something else. Okay, how should I write this? Let phi be a vector space. Consider the subset which is the empty set. Note that every subspace of V contains the empty set, because the empty set is a subset of every set. In particular, the empty set is also a subset of every subspace of V, and among those subspaces there is one that is the smallest. In particular, the empty set is also contained in the subspace consisting of only the zero vector, and we know that if we take the intersection of all subspaces of V without restricting them in any way, then the intersection is this itself, because this is the absolute smallest subspace in any vector space. Hence, by the definition of I was going to say logarithmic integral, sorry, this is Li. Hence, Li of the empty set is the zero space, which is also sometimes written like this. Okay, so you may think that so much of work just for this case, but this case is necessary. We will see when we get to the theory of dimensions. We are going towards that, but it will take some time to reach those parts. So you can see that when S is non-empty, then our linear span, which is nothing but Herstein's linear span, is a subspace. In this case, when S is empty, then also it's a subspace, it's the zero space. If you want, you can mention that fact also, that if S is any subset of a vector space V, then the linear span, our linear span, is a subspace of V, irrespective of whether S is empty or non-empty. Now next, there is a lemma, actual lemma from the book. If S and T are subsets of V, then the following facts are true, where V of course is a vector space, S a subset of T, this statement implies that the linear span of S is a subset of the linear span of T. 2. The linear span of the union of S and T turns out to be the sum of the linear span of S and the linear span of T. And 3. The linear span of the linear span of S is nothing but the linear span of S. Now that we have a general linear span, we are going to state a similar lemma where the statements, everything will be almost like this, but in place of ordinary linear span we will write Li, and we will prove that and derive this. So this is again some lemma. If now you can understand that we are also going to write S and T are subsets of V, but because Herstein has defined linear span only for non-empty sets, so in the context of this lemma, S and T are non-empty, because otherwise these symbols don't make sense, they are meaningless. However, for us, S and T are truly general subsets. If S and T are subsets of phi, then 1, again this implies, in fact proving these statements will be somewhat easier than this. The first one is particularly easy. There was no need to make these artificial definitions lemmas corollaries if the general definition was there. Okay, let us now prove this. Okay, so in number 1 we have to prove this, right? We have S as a subset of T. Okay. Since Li of T is a subspace of V, containing T and T contains S, we have this. Okay, there are one or two things here to see. First of all, we are writing that Li of T is a subspace of V. This is a fact we have proved, we have already proved. And see, to actually be able to write this statement, we need both the things. First of all, that lemma where we proved that when S is non-empty, then Li of S is a subspace of V, and that is because in this case, this which is a subspace of V that we have already proved previously, and in this case when S is empty, here also Li of S, which is the zero space, that is a subspace of V. So whether S is empty or non-empty does not matter, or in fact we are talking about T, no, so whether T is empty or non-empty, this is a subspace of V, that is correct. And since by definition it is the intersection of all subspaces of V containing T, so this also contains T and T contains S, so this now has become a subspace of V that contains S. Now if one considers Li of S, this is the intersection of all subspaces of V containing S, and of which this is 1. So clearly this will be contained in this, because here all subspaces of V containing S are being considered. Hence, and that's how we have this. Why I said this is easier to prove than this one, it's because if you want to prove this, you have to consider those linear combinations and all those things. Here, however, because of the nature of the definition of Li, the things are slightly easier. Easier to write at least. Okay, then the second part, Li of S union T is Li of S plus Li of T. One half of this statement can be concluded from here itself by, or in fact let's just write that also, since S is contained in S union T and T is also contained in S union T, part 1 gives us Li of S contained in Li of S union T and Li of T is also contained in Li of S union T. So their sum will also be contained in Li of S union T. But why? Let us first write and then see why. When you consider an element in this sum, that element is the sum of one element from here and one element from here. Since those two elements belong to Li of S and Li of T respectively, which themselves are contained in this bigger set. So those two vectors both belong to Li of S union T, and because Li of S union T is a subspace, so that's why their sum belongs to this, and that is why this is contained in this, which we are not writing so much here because that is understood. Now we have to prove the converse. For the converse, however, we have to go down to the level of elements. Simply considering sets will not be enough. Now for the converse, if S is empty, say, okay, then in fact the equality itself is true. How? Because in that case this is nothing but Li of T, which one can write as Li of T plus the zero space. This is any subspace and this is the zero space. If you take their sum, then what will there be in that sum? Vectors which look like this. One vector from here plus the zero vector, which is that vector itself. So this sum is Li of T itself, and we have already seen that it becomes Li of the empty set, or in fact I should have written 0 here and Li of T here. Similarly, if T is empty, then also one gets equality. So assume that both are non-empty. Okay, if both S and T are non-empty, then we are back to the statement of the previous, the actual lemma given in the text. That means in this case Li reduces to L. Okay, however we are not proving the equality entirely. I mean, we already have this. Now we want the converse. Okay, then S union T is also non-empty. So in this case we need to prove, or in fact it's enough to prove that this is contained in this. Okay, so let us start by taking one element here. Let say gamma 1 W1 plus gamma 2 W2 etc. plus gamma n Wn belong to L of S union T, where the W's belong to S union T and the gammas are coming from the field. If the W's all belong to S, that is also a possibility, then this element can be written as, we have to wrap this up totally. We can recall what the third one later when we will prove it. This can be written as plus 0. Now because all the Wi's belong to S, so by definition of linear span, this first vector belongs to L of S, and 0 of course belongs to L of T, because 0 belongs to any space, any subspace, so this is a subspace, so 0 belongs to this. If on the other hand the W's belong to, all of them belong to T, Now here the first one belongs to the linear span of S, and the second one, because now all the Ws belong to T, belongs to the linear span of T. So we now assume that both T and S have at least one W. I mean, each one of them has at least one W. How to write that nicely? Okay, we can write like this. The set of the W's intersects both S and T. Let the first intersection be of course they are going to be some W's only, but we don't know which I1, I2, I mean which one of these suffixes will come here. I say let us take alpha, and the other intersection this is the problem. When we get down to the level of elements, we have to write a lot, but no other choice. Wj1, Wj2, J beta, and where definitely alpha plus beta is n. Oh, alpha plus beta is not okay. This actually will not help me, na? This actually will not help me. Because there may be common vectors among these vectors also. So instead of taking T here, this S is fine, but here I am going to consider T minus S, because then only I will get distinct vectors. And what is the justification for assuming this? We are now considering, so these are the two cases we have already considered. Here all the elements belong to S, here all the elements belong to T. So that means now something is not right. It feels like I am missing something. Oh, there, okay. There is no need to consider this second case. we can see what is going on here. I mean, if you have some elements in S, say, then you take them together, and if you have some extra elements which are not in S, then you take them separately. They will belong to the linear span of T, and this will belong to the linear span of S. So it's about being in S and not being in S. Okay. If still I am getting confused. This is S, this is T, right? So if I have that all the W's here, then that case we have written here. So that means now if all the W's are not in S, okay. Yes. Now suppose this is not a subset of S. Yes. Then some of the W's will be in T, but the question is, can it happen that all the W's belong to T and nothing is there in S? That is also a possibility. So we should have accounted for that before writing this. Sorry for this confusion, but I need to make sure what I am writing actually makes sense. Then 1 similarly has, you have already seen the calculation once, okay. Similarly has L of S union T contained in not this one, gamma W1 plus gamma 2 W2 plus gamma N Wn plus L of T. Now assume that this is neither contained in S nor contained in T. Now there will be some w in S and some w's in T. Maybe there are some common w's. We will take care of them. Let intersection SB T minus S. Okay. Because everything is not in T, so we will have something here. And because everything also is not in S, we will have something here. Keep in mind that our W's are coming from S union T. So nothing is coming from outside of both S and T. So each one of them should belong to either S or T. So that's why this makes sense. Then, now we can finally write gamma 1 W1 plus gamma n Wn. Because of this confusion, we have lost a lot of time. Now it can be written as a sum of two linear combinations. One of these and the other of these. These are in S, so this linear combination belongs to L of S and this one belongs to L of T. So in any case we have L of S union T is contained in L of S plus L of T. Thus, the reverse inclusion we have shown for